In this video, we'll discuss the simplex method for maximization problems. Now, we've talked about linear programming with two variables before, where we're trying to maximize, and we use the inequalities of with two variables, graph them, find the vertices, and then plug those into the objective function to find the maximum or minimum value created. Question is, what happens when we have more than two variables, or if our inequalities become so large it's hard to tell where those vertices are? That's where the simplex method for maximization can be very helpful. Now, it is used primarily for maximization problems because that's the standard form of linear programming. That means that our inequalities have to be less than or equal to, and our solution values for the objective function have to be greater than or equal to 0. And what we do is we have to first create a simplex tableau. Now, the simplex tableau is an augmented matrix created with constraint equations and this form of the objective function. And what you see here is that we have the z value, but then we've moved over the other values from the objective function to the same side, so they're the opposite value. Maybe you're asking, what is a constraint equation? It is those constraint inequalities plus some slack, and we use a variable for the slack of each inequality that's inside of our linear program. So let's look at an example. Here's a constraint inequality. If we wanted to make this become an equation, what we would do is we would add a slack variable, and that slack variable picks up the difference created by between this expression and the value of 12. So when we're creating our simplex tableau, say here's our example, we have our objective function. We're told that our x values are both greater than 0 or equal to 0 in this objective function, and we have our constraint inequalities. What we want to do for the simplex tableau is we want to create that augmented matrix with the equations and the opposite coefficients of the objective function. So let's create the constraint equations. All I do is I give each inequality its own slack variable. So the first one gets S1, the second one gets S2, the third inequality gets S3 to make an equation. If there was a fourth inequality, there'd be an S4. And now we just plug these things into an augmented matrix. And just pay attention. I have no values for S2 and S3. That means that they're going to become zeros in my augmented matrix. Then I pay attention each row. If I'm missing something, I just put a 0 in its place. I get to the third row, I put zeros in for S1 and S2. Now, this is one of the unique pieces then as I get to creating the simplex tableau. I now need to pay attention to my objective function. I'm not going to use it in its current form. I'm going to move everything to the same side of z and set it equal to 0. That means that instead of having positive 6, I have negative 6. Instead of negative 2, I have positive 2. And then I have to think about those slack variables still, which are 0, 0, and 0. And currently, I'm going to use 0 to start off my maximization because I don't know that value yet. So if I want to look at the parts, again, as I simplify my simplex tableau, my bottom right value becomes the maximization value. It'll tell me what is the objective function's value, that z value. And if I look at it, my current basic variables are S1, S2, and S3 because they are the pivots. They have values of 1 and zeros in the rest of the column. And that means my non-basics are X1 and X2. So if I was to look at what is the current solution, I would say that it is 0, 0, 20, 14, 32, 0. The problem is that's not very helpful because my solutions are on the slack variables. And I don't want them on the slack variables, I need them on the x values. So how do we do that? Well, our goal in trying to help us find that maximization is we're going to take that bottom row and get rid of all the negative values on the bottom row. So if we look back here, you can see we had this negative. That's part of the problem. We need to get rid of that negative value. So what are the steps? First thing, create the constraint equations. We've shown how to do that. Second step, create the simplex tableau. We've shown how to do that. Third thing, we're going to choose the most negative entry in that last row, excluding what becomes the z value. that most negative entry is our entering column. If there's more than one, you get to choose if they're equal to each other. Now what we're going to do is we're going to look up and down that column, and each entry in the column, we're going to take its corresponding b value and divide by that entry. What we're going to choose is the smallest positive value, and that's going to become the departing row. It has to be positive, and it's going to be the smallest of them. If there's no positive values, we can't find a maximization, and you can say there's no solution. Now what we're going to do is we're going to convert first that Aij entry into the pivot, so it's going to become 1, and we're going to use elementary row operations to make every other entry in that column become zeros. And we keep doing that until we no longer have a negative value in the last row of our Simplex Tableau. That'll tell us then what are the solutions and what is the maximization of that function. So let's go back to the example we used earlier. In this example, we created the constraint equations. We created the Simplex Tableau. Now we can ask ourselves, where's that departing row? Well, it's going to be right here because it's a -6. Now I want to look and say, well, which of these will become my departing column? And it'll actually be the second. Why? Because if I check each b value divided by each value in my first column, I'll see that I have that the first row gives me 20, the second row gives me 3.5, and the third row gives me 5 1/3. Well, 3.5 is the smallest value, so that's the value I want to pivot. So what I like to do is I like to actually make that become the true pivot. I turn it into 1 to start with. So I'm going to multiply that entire row by 1/4. Now I can go through and I can use elementary row operations on each of the other 3 rows. The first one, I'd end up subtracting row 2. The third row, I'd end up subtracting 6 times row 2. And in the fourth row, I end up adding 6 times row 2. So I'm going to perform all these operations at once because we've talked about how to do elementary row operations before. So here's the new Simplex Tableau. Now I'll look at it and say, okay, I want to go to my last row, and I'm like, oh, right here I still have a negative value. So this becomes my new entering column. Now I'm going to go through and I'm going to check each of my 3 rows and figure out which one becomes my departing row. And in this case, it will be the third row. So again, why is that the case? 33/2 divided by 11/4 is 6. I can't do the middle row because that's a negative, and I've already created an entry. I've created the pivot here, but that negative value makes it not possible. So I'll look at the third row, and 11 divided by 11/2 is 2, and 2 is my smallest value. So what I like to do, again, I'm going to multiply by 2 11s, make that entire row become simplified so that becomes a 1. And now I can simplify my other 3 rows. I'm going to subtract 11/4 of row 3 to the first row. I'm going to add 3/4 of row 3 to the second row. And I'm going to add 5/2 of row 3 to the fourth row. Now when I simplify, if I look, my last row, all positive. So that means that at this point, I've solved my maximization problem. So what does this mean? What this means is that my x1, because it's got the 1, is 5. x2, so look in here, x2, its value is 2. s1, that's actually the third pivot, is 11. And then s3 and s4 now are non-basic variables, so they have values of 0. And the maximization of my function is 26. Well, why is it 26? Well, let me take my x1 and my x2 value, plug them in to my objective function. 30 minus 4 is 26. So here I've used the Simplex Tableau to find the solution. Now, if you wanted to double check, because this is a 2-variable problem, I could use my constraint inequalities. I could actually graph it with the inequalities. I find my 5 points, but I know 0, 0 is not going to maximize this, so I can check the other 4. Again, I had my 1 that I already did. I can take 4, 8, plug it in, and that gives me positive 8. I can do 3.5, 0, that gives me 21. And then if I do 0, 10, I get negative 20. So again, my greatest value is the one where my x1 is 5 and my x2 is 2.